blue is what we call dark matter. The reasons dark matter feels mysterious and even a bit frightening are twofold. First, it defies our understanding of matter and energy as we know them. Our universe is built on atoms and particles, yet dark matter does not correspond to any of those familiar entities. Second, dark matter poses profound questions about the very fabric of reality, challenging everything we thought we understood about the universe's composition. This mystery continues to inspire intense scientific inquiry. Countless researchers are engaged in experiments to identify the properties of dark matter and ultimately to discover what it is made of. As a leading player in the cosmic narrative, dark matter holds the key not only to understanding the universe's structure, but also to grasping the fundamental laws that govern it. The search for dark matter remains one of the most thrilling quests in modern astrophysics, continually pushing the boundaries of our knowledge. Dark matter is one of the universe's great mysteries, making up about 27% of everything we know exists. Although it is invisible and does not emit light, dark matter exerts a gravitational influence that shapes the cosmos on a grand scale. Its presence is fundamental in forming structures, such as galaxies, clusters of galaxies, and the cosmic web that connects them. This web-like structure of the universe is a result of dark matter's gravitational pull, which serves as a framework where visible matter, like stars and gas, gathers and forms the galaxies we can observe. When we consider how galaxies form and evolve, it's clear that dark matter plays a pivotal role. Early in the universe's history, tiny fluctuations in density allowed dark matter to collapse and form clumps. These clumps acted like seeds, drawing in regular matter due to their gravitational attraction. As these ordinary materials accumulated, galaxies began to take shape around these dark matter halos. This means that every galaxy is like a bright island in a dark sea, with the dark matter providing the unseen structure and stability required for star formation and galactic activity. Moreover, dark matter influences not just the formation of galaxies, but their interaction as well. Galaxies are not isolated. They exist in clusters that can consist of hundreds or even thousands of galaxies. The gravitational pull of dark matter helps bind these clusters together, affecting their motions and the dynamics within them. Observations indicate that the majority of the mass in these clusters is in the form of dark matter, reinforcing its critical role in the universe's large-scale structure. Finally, the expansion of the universe itself is influenced by dark matter. While dark energy drives the accelerated expansion, dark matter helps slow it down through its gravitational effects. This complex interplay of forces highlights dark matter's vital role in maintaining the balance of the cosmos. The continued study of dark matter not only enhances our understanding of how the universe operates, but also inspires a deeper appreciation for the intricate dance of particles and forces that make up our vast universe. Dark matter, an elusive component of our universe, makes up about 27% of its total matter-energy content. Despite its prevalence, dark matter remains one of the greatest mysteries in cosmology. Various theories abound, each offering different candidates for this invisible substance, from exotic particles to modified gravity theories. One prominent theory proposes that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact with normal matter through gravity and perhaps through weak nuclear forces. Since they interact so weakly, they would be difficult to detect directly. Scientists have designed numerous experiments deep underground and even in space to try to catch a glimpse of these elusive entities, but so far they remain undetected. Another intriguing candidate is axions, extremely light particles thought to arise from certain theoretical frameworks in particle physics. Axions are peculiar because they could explain not only dark matter, but also certain peculiarities in the behavior of magnetic fields. If they exist, axions would form a kind of background energy field, subtly influencing the universe's structure without being noticed directly. Research into axions continues to unfold as scientists explore ways to discover these quirky particles. Additionally, there are theories that suggest dark matter might not be a particle at all, but rather an alteration in our understanding of gravity itself. Modified gravity theories propose that the laws of gravity as we know them may not apply at cosmic scales. These theories, such as MOND, suggest that we need to rethink our gravitational laws to account for the observed effects attributed to dark matter. Each theory presents a unique perspective on dark matter, reflecting the ongoing quest to unlock the secrets of our universe. The search is not just for answers, but for a deeper understanding of the cosmos that surrounds us. Dark matter is an elusive substance that makes up a significant portion of the universe, yet it does not interact with ordinary matter in the way we might expect. Unlike the atoms that compose the stars, planets, and ourselves, dark matter does not emit, absorb, or reflect light. This characteristic means that it cannot be detected by traditional means of observation, which rely on electromagnetic radiation. As a result, dark matter's presence is inferred indirectly from its gravitational effects on visible matter. This lack of direct interaction can imply several things about our cosmos. If dark matter were to interact with ordinary matter, even slightly, we might expect to see signs of this interaction in particle colliders or through various detection experiments. However, the minimal interaction suggests that dark matter particles are incredibly weakly interacting, or perhaps they have their own set of fundamental forces. Thus, while ordinary matter forms the building blocks of the stuff we see, dark matter operates under a different set of rules. Understanding dark matter's properties is vital for our comprehension of the universe's structure. It accounts for about 27% of the total mass energy content of the universe, influencing how galaxies form and bind together. The gravitational lensing effect, where light from distant objects bends around massive dark matter structures, is one of the clues astronomers use to map dark matter distribution across the cosmos. This complex interplay provides insight into evolutionary processes on a grand scale. The limited interactions between dark matter and ordinary matter lead to profound implications. They challenge our current understanding of physics and suggest enigmatic properties of dark matter that remain to be fully unraveled. As researchers continue to explore these interactions, they blaze trails toward uncovering one of the universe's most compelling mysteries, potentially reshaping our view of reality. Astrophysicists refer to dark matter as invisible because it does not emit, absorb, or reflect light, making it undetectable through traditional telescopes. Instead, it interacts with ordinary matter and radiation only via gravity. This elusive nature is one of the primary reasons why dark matter remains a mystery. We can see its gravitational effects on galaxies and galaxy clusters, but we cannot observe the substance itself. Think of it like trying to detect the presence of a ghost in a room. You can't see it, but when the curtains flutter or an object moves, you know something is there. The challenges posed by this invisibility are significant for scientists. For one, it complicates the process of identifying the particles that make up dark matter. Since these particles do not interact with light or other forms of electromagnetic radiation, experiments designed to detect dark matter directly often have to be set up far underground or shielded from cosmic rays, adding layers of complexity to the research. Moreover, the inability to observe dark matter directly means that astrophysicists must rely heavily on indirect evidence, drawing conclusions based on the gravitational influences it appears to exert on visible matter. Moreover, the search for dark matter involves innovative techniques and technologies. Some researchers aim to create high-energy collisions in particle accelerators, hoping to generate dark matter particles that can be captured and studied. Others are looking into delicate detectors that can sense the minuscule effects of dark matter interactions. Each approach brings with it a series of uncertainties and requires careful interpretation of results, which often leads to debates within the scientific community about the nature of these enigmatic particles. Despite these challenges, the pursuit of understanding dark matter is a driving force in modern astrophysics. The quest not only deepens our understanding of the universe, but also raises profound questions about the very fabric of reality. As observations continue to accumulate and new technologies emerge, the hope is that one day dark matter will no longer remain a ghostly presence but will be revealed as a fundamental component of the cosmos. Dark matter, the mysterious substance that makes up about 27% of the universe, plays a crucial role in shaping its fate. Unlike normal matter, dark matter does not emit, absorb, or reflect light. Instead, it interacts with regular matter through gravity. This gravitational influence is essential for the structure and evolution of the cosmos. As galaxies form and evolve, dark matter serves as a framework that holds them together. As we look to the future, dark matter impacts the potential scenarios for the ultimate fate of the universe. One possibility is the Big Freeze, where the universe continues to expand indefinitely. In this scenario, galaxies drift apart, stars burn out, and the cosmos becomes cold and dark. Dark matter, contributing to the expansion rate, could help determine how quickly this spread occurs. If dark energy, another mysterious force, continues to drive the universe's expansion faster, dark matter's gravitational forces may either resist this expansion or play an invaluable role in how structure persists over time. Alternatively, if certain properties of dark matter were to change, it could lead to different outcomes. For instance, if dark matter were to behave differently under certain conditions, it might enhance gravitational clumping, potentially leading to a universe where galaxies are pulled back together. This could result in a big crunch, where the expansion reverses and everything collapses back into a singular point. Although this scenario currently seems unlikely, ongoing research into dark matter could change our understanding about its properties and interactions. Ultimately, the fate of our universe is linked to its unseen components. As we delve deeper into the mysteries of dark matter and its effects, we might uncover new insights that could reshape our understanding of cosmic destiny. Each discovery about dark matter offers an opportunity to appreciate the intricate, unseen forces that govern our cosmos, piquing our curiosity about the future of everything we see and beyond. Dark matter is one of the most intriguing concepts in modern astrophysics, as it serves as a key to understanding several unexplained phenomena in the universe. One of the most prominent mysteries is the rotation rates of galaxies. When scientists observe how fast galaxies spin, they notice something puzzling. The outer regions of galaxies rotate much faster than would be expected based solely on the amount of visible matter. This discrepancy suggests that there is an unseen mass, dark matter, providing the gravitational pull necessary to keep these stars in their fast orbits. Another enigmatic phenomenon linked to dark matter is gravitational lensing. As light travels across the cosmos, it can be bent by the gravitational field of massive objects like galaxies or clusters of galaxies. This bending of light can create distorted or multiplied images of distant celestial bodies. Observations reveal that the amount of lensing exceeds what we would expect from the visible matter alone. Dark matter, spread throughout and beyond these massive structures, is the explanation for this unexpected bending, indicating vast reservoirs of unseen mass. Additionally, dark matter plays a crucial role in the formation of large-scale structures in the universe. The cosmic web of galaxies, clusters, and voids seems too intricate to have formed purely from visible matter. Computer simulations that include dark matter reveal that its presence allows for the gravitational scaffolding needed to form these large structures over billions of years. Without dark matter influencing the formation process, the universe as we know it would look vastly different, with fewer galaxies clustered together. Finally, the cosmic microwave background radiation, the afterglow of the Big Bang, provides another piece of evidence for dark matter. Tiny fluctuations in temperature observed in this ancient radiation can be attributed to the gravitational effects of dark matter. These fluctuations reflect the density variations in the early universe, where dark matter played a critical role in shaping the cosmos from its infancy. All these phenomena highlight the fundamental importance of dark matter in our understanding of the universe, leaving many questions still ripe for exploration. The existence of dark matter has captivated astronomers and physicists for decades, primarily due to compelling evidence that suggests its presence throughout the universe. One of the most striking pieces of evidence comes from the behavior of galaxies. When astronomers measure the rotation speeds of galaxies, they observe something perplexing. The outer regions of galaxies rotate much faster than expected. According to the laws of gravity, if only visible matter were present, the outer stars should be moving more slowly. This discrepancy hints at an unseen mass, dark matter, exerting gravitational influence. Another key piece of evidence arises from the study of galaxy clusters. When scientists observe these massive formations, the visible mass, made up of the stars and gas, only accounts for a fraction of the total mass needed to hold the cluster together. The gravitational effects, such as the way galaxies within the cluster move and the bending of light from distant objects, a phenomenon known as gravitational lensing, indicate that there is much more mass than we can see. This unseen mass is attributed to dark matter, which plays a crucial role in the formation and structure of the universe. Cosmic microwave background radiation provides further support for dark matter. This radiation is a relic from the early universe, and its study reveals fluctuations in temperature that correspond to density variations in the early cosmos. The pattern of these fluctuations suggests a universe dominated by dark matter, which influenced how regular matter clumped together after the Big Bang. The data collected from space observatories like the Wilkinson Microwave Anisotropy Probe solidifies our understanding of dark matter's role in shaping the early universe. Together, these pieces of evidence form a compelling case for dark matter's existence. While we may not be able to directly observe dark matter, its influence is felt everywhere, from the intricate dance of galaxies to the structure of cosmic radiation. As we continue to explore the universe, dark matter remains one of the most intriguing mysteries, inviting scientists to unravel its secrets and understand our cosmic neighborhood more fully. Black holes and dark matter are both fascinating components of the universe, each playing crucial roles in cosmic evolution. Black holes, regions in space where gravity is so strong that not even light can escape, are formed from the remnants of massive stars that have collapsed. Dark matter, on the other hand, is an invisible substance that makes up about 27% of the universe's mass. It does not emit, absorb, or reflect light, making it difficult to detect directly. However, its presence is inferred from gravitational effects on visible matter, such as stars and galaxies. Research shows that black holes and dark matter interact primarily through gravity. As galaxies evolve, dark matter helps to shape their formation and structure, creating gravitational wells that attract normal matter and eventually form stars. These black holes, especially supermassive ones found at the centers of galaxies, influence their surrounding environment. They can affect star formation rates and gas dynamics, which are crucial for galactic evolution. Interestingly, black holes might also influence the distribution of dark matter within galaxies. As black holes consume material, they emit energy in the form of radiation, altering the dynamics of the surrounding dark matter. This interaction could lead to different configurations of dark matter in galaxies, contributing to the variety we observe across the universe. The interplay between black holes and dark matter presents a more complex picture of cosmic evolution than scientists once thought. By studying how these entities interact, astronomers gain deeper insights into the history and future of our universe, revealing that the cosmos is not just filled with stars and planets, but intricately woven with unseen forces and mysterious phenomena. As we advance our understanding, the relationship between these two cosmic powers will undoubtedly yield more surprises in the grand tapestry of our universe's history. Gamma-ray bursts are intense flashes of gamma rays, the most energetic form of light in the universe. They typically last from a few milliseconds to several minutes, and are thought to be caused by catastrophic cosmic events, such as the explosion of massive stars in supernova or the collision of neutron stars. These bursts can release as much energy in a few seconds as the Sun will emit over its entire 10 billion-year lifetime. One of the reasons gamma-ray bursts are considered terrifying is their sheer power. A single burst can emit more energy than the Sun will produce throughout its entire existence. If a gamma-ray burst were to occur relatively close to Earth, say within a few thousand light-years, the gamma rays could potentially deplete the ozone layer, exposing our planet to harmful ultraviolet radiation. This could lead to devastating consequences for life on Earth. Moreover, they occur without warning, appearing suddenly and unpredictably. Scientists have detected these bursts from billions of light-years away, showcasing their ability to travel vast distances through space. Each new observation adds layers to our understanding, but the unpredictability of these events keeps the scientific community on high alert regarding their potential impact on Earth. While gamma-ray bursts are terrifying due to their potential effects, they also serve as a reminder of the dynamic and violent nature of the universe. They provide scientists with invaluable information about the life cycles of stars and the conditions surrounding stellar explosions. Each discovery helps uncover the secrets of the cosmos, ensuring that our understanding continues to evolve alongside the mysteries of the universe. To understand the remarkable bursts of energy in the universe, we must look at phenomena such as supernovae and gamma-ray bursts. At their core, these events are rooted in the life cycles of stars. Stars, like our own sun, spend most of their lives converting hydrogen into helium through nuclear fusion, releasing energy in the process. But when a star exhausts its fuel, dramatic changes occur that lead to stunning explosions. In the case of a supernova, when a massive star has burned through its core's nuclear fuel, it can no longer support its own weight. The core collapses under immense gravity, causing a rebound effect that sends shockwaves outward. This catastrophic explosion can outshine an entire galaxy for a brief period, releasing more energy than the sun will emit in its entire lifetime. In this moment, elements are forged and expelled into space, seeding the universe with the building blocks for new stars and planets. Gamma-ray bursts, on the other hand, represent some of the most energetic events observed in the universe. These bursts can occur when a massive star collapses into a black hole or when two neutron stars merge. They release beams of gamma rays that can last from milliseconds to several minutes. What's fascinating is that while only a tiny fraction of the energy is cast in our direction, that energy far exceeds the luminosity of an entire galaxy, making them incredibly powerful events. Both phenomena, the supernova and gamma-ray burst, highlight the fascinating interplay of gravity, energy, and stellar evolution. They remind us of the dynamic and ever-changing nature of the cosmos, where powerful bursts of energy can forge the very elements that make up our world and shape the universe as we know it. These immense bursts are not just spectacular fireworks in the night sky. They are vital processes that drive the evolution of the universe itself. Gamma-ray bursts are among the most powerful explosions in the universe, often originating from massive stars collapsing into black holes or from the merger of neutron stars. These events are quite rare on a universal scale. On average, astronomers estimate that gamma-ray bursts occur about once every 100 years in a galaxy like ours, the Milky Way. That means while they are frequent throughout the universe, they are relatively uncommon in any single galaxy. Now, considering the vastness of space, the likelihood of a gamma-ray burst directly affecting Earth is exceedingly low. Our planet is shielded by an atmosphere and a magnetic field, which provide protection against many forms of cosmic radiation. Even if a gamma-ray burst were to occur in our vicinity, say within a few thousand light years, it would need to be oriented just right to have any significant impact on our atmosphere. Thankfully, there have been no gamma-ray bursts close enough in our galaxy that posed any real threat. As we look into the cosmic scales of time and space, it's fascinating to realize that the energy released by a gamma-ray burst can outshine entire galaxies for brief moments, lasting only seconds to a few minutes. These bursts emit intense bursts of gamma radiation and can sometimes be seen from vast distances. Their power, while breathtaking, is generally too far removed to worry us here on Earth. In conclusion, while gamma-ray bursts are fascinating phenomena that deserve our interest, they pose little danger to our planet. The universe may be brimming with energy and excitement, but for now, we can observe these bursts as a reminder of the dynamic and ever-changing cosmos, knowing that Earth remains in a relatively safe spot in this grand celestial drama. Gamma-ray bursts are among the most powerful explosions in the universe, releasing immense amounts of energy within a very short time. To put this in perspective, a single gamma-ray burst can emit as much energy in a few seconds as the Sun will produce over its entire 10 billion-year lifetime. If such an event were to occur close to Earth, it could indeed have catastrophic effects on a planetary scale. One of the primary concerns with a nearby gamma-ray burst is the impact on our atmosphere. These bursts emit high-energy gamma rays which can strip away the ozone layer, the protective shield that absorbs the majority of the Sun's harmful ultraviolet radiation. Without this layer, increased levels of UV radiation would reach the surface, leading to a surge in skin cancers, damaging effects on ecosystems, and disruptions in food chains. The consequences could extend beyond individual health issues, affecting agriculture and the environment on a global scale. Moreover, gamma-ray bursts could initiate a cascade of effects in our climate. The intense radiation could lead to chemical reactions in the atmosphere that might cool the planet temporarily due to particles being expelled into the stratosphere, blocking sunlight. This phenomenon could trigger dramatic climate shifts, causing temperature drops and altering weather patterns. Such changes would challenge the delicate balance of our ecosystems, making survival increasingly difficult for many species. While the probability of a gamma-ray burst occurring close enough to Earth to cause such catastrophic effects is exceedingly low, these events remind us of the vast universe we inhabit. They serve as a stark example of the potential dangers lurking beyond our atmosphere, emphasizing the importance of understanding cosmic phenomena and their effects on our planet. The study of gamma-ray bursts not only fascinates astronomers, but also provides valuable insights into the workings of our universe and the fragility of life on Earth. Gamma-ray bursts are among the most powerful explosions in the universe, unleashing energy that can outshine entire galaxies in mere moments. Although these cosmic events are incredibly rare, they pose a potential threat to life on Earth, primarily due to their intense radiation. When a gamma-ray burst occurs within a distance of approximately 6,000 light-years, the effects could be catastrophic for our planet. The high-energy gamma rays could strip away the ozone layer, a critical shield that protects us from harmful ultraviolet radiation from the sun. Moreover, if a gamma-ray burst were to occur nearby, it could lead to severe environmental consequences. With the ozone layer compromised, increased levels of ultraviolet radiation would penetrate the Earth's atmosphere, leading to harmful impacts on living organisms. This could cause a dramatic rise in skin cancer cases in humans, disrupt ecosystems, and threaten various species, particularly those that are sensitive to radiation. Interestingly, scientists believe that such bursts occur due to the collapse of massive stars or the merger of neutron stars. These events create jets of gamma rays that shoot out into space, and if aligned with Earth, the impact could be devastating. While the probability of a gamma-ray burst directly affecting our planet is low, the sheer energy involved leaves us pondering the vulnerability of life in the cosmos. Despite the potential risks, it's important to note that life on Earth has endured many cosmic events over the eons. Our planet has weathered asteroid impacts, supernova explosions, and even climate changes, while gamma-ray bursts represent a fascinating and alarming aspect of our universe. They also remind us of the resilience of life and the intricate balance that exists within cosmic forces. Gamma-ray bursts, or GRBs, are among the most energetic events in the universe. These bursts of gamma rays signify some of the most powerful explosions known, and they primarily come in two distinct types: long-duration and short-duration gamma-ray bursts. The classification is based mainly on their duration, with long bursts lasting more than 2 seconds and short ones lasting less than 2 seconds. Long-duration gamma-ray bursts often result from the collapse of massive stars. When a large star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. This collapse can lead to the formation of a black hole, unleashing a colossal amount of energy that is observed as a GRB. A notable example is the burst designated GRB 980425, which likely originated from a supernova in a galaxy far from our own, illustrating the connection between GRBs and stellar evolution. On the other hand, short-duration gamma-ray bursts are believed to come from the merger of compact objects, like two neutron stars or a neutron star and a black hole. These events create gravitational waves in addition to bursts of gamma rays. One remarkable example is GRB 170817, which was detected in August 2017. This event was particularly groundbreaking as it was observed simultaneously with gravitational waves, providing invaluable insights into the nature of such cosmic collisions and marking a significant milestone in multi-messenger astronomy. Both types of gamma-ray bursts serve as magnificent cosmic beacons, allowing astronomers to study the fundamental processes of the universe. Their immense energy and the distances they can span mean that GRBs not only deepen our understanding of stellar life cycles and cosmic events, but also challenge our grasp of the universe's structure and evolution. Through continued observation and study, these bursts remain a vital area of research, revealing secrets about the universe that still captivate scientists and curious minds alike. Gamma-ray bursts, the most intense and energetic explosions known in the universe, have captured the attention of scientists since their discovery in the late 20th century. Observations began with military satellites originally designed to monitor nuclear tests. They detected these high-energy radiation bursts from far-off galaxies, and the sheer power of these events was astonishing. In those early days, the bursts felt almost mythic, portents of cosmic violence that defied much of what we understood about celestial mechanics. As telescopes improved and technology advanced, scientists learned to pinpoint the origins of these bursts with greater accuracy. Instruments like the SWIFT satellite, launched in 2004, played a pivotal role in detecting gamma-ray bursts within seconds of their occurrence. SWIFT allows astronomers to not only measure the gamma rays, but also observe the afterglow in other wavelengths, such as X-rays and visible light. This multi-wavelength approach has been crucial in unraveling the life cycle of a gamma-ray burst, revealing that they often result from massive star explosions or the collisions of dense neutron stars. Through extensive study, researchers discovered that gamma-ray bursts are typically mere seconds to a few minutes long, with energy output dazzlingly more powerful than billions of stars combined. This means that if a gamma-ray burst occurred close to Earth, even within 2,000 light-years, it could significantly affect our planet's atmosphere and potentially disrupt life as we know it. The fearsome reputation of these bursts essentially stems from their colossal